For the compound infinite series that is shown in this example, we want to see whether there is a quick way to solve this infinite series. Does it converge? And can we find a closed form formula for the finite version of this summation or not? To answer this question, let's focus on the terms of this series, starting with the first term. So there is a quick trick to just utilize the properties in numerator and denominator in the first term. If you focus on this first term, there is 1 plus 3 in numerator divided by 5 plus 7 in denominator. So I can write it 1 plus 3, and remember that 3 is just 2 times 2 minus 1. So the most important thing about that is we have 2 terms in numerator and 2 terms in denominator effectively, and that 2 appears here as well. In denominator, I have 5 that I can write it 1 plus 4. And I have 7 that I can write it as 3 plus 4. So if I just write it in a better way, it's 1 plus 3 as before, and then I have 1 plus 3, and then I have 2 times 4. So 2 times 4, that effectively I can write it as 2 times 2 as well. So in summary, what I can show for, let's say if I write it at the here, so it's 1 plus 3 divided by 1 plus 3, and then we have 2 times 2 to the power 2. Okay, so let's keep that in mind. For the next term, which is the second term, I have 1 plus 3 plus 5 in numerator, and then 7 plus 9 plus 11 in denominator. So I can use the same trick. Just bear in mind we have 3 terms, so we have 3 terms both in numerator and denominator. And the nice thing about this whole thing is it's 1 plus 3, and 5 can be written as 2 times 3 minus 1. See, the number of terms is showing up as defining the last term in numerator. For denominator, I can write it 7 as 1 plus 6, and 9 as 3 plus 6, and for 11, I can write it 5 plus 6. So it's going to be 5 plus 6. Now what I can do is again 1 plus 3 plus 5 divide by 1 plus 3 plus 5, and I have 6, 6, 6 repeated 3 times, so it's going to be 3 times 6, and 6 can be written as 2 times 3. So we go back to writing this whole thing as 2 times 3 to the power 2. So let's do it. So it's 2 times 3 to the power 2. Interesting. So we have 2 terms. 2 shows up here to the power 2 multiplied by 2. We have 3 terms. 3 shows up here to the power 2 multiplied by 2. No wonder that if I keep doing this, for the third term, which is 1 plus 3 plus 5 plus 7, that are 4 terms in numerator and denominator, I have exactly the same property showing up. So it would be 1 plus 3 plus 5 plus 7, and instead of 9 I can write 1 plus 8, instead of 11 I can write 3 plus 8, and 13 is 5 plus 8, 15 is 7 plus 8. So again the same thing is going on here in denominator as before, 1 plus 3 plus 5 plus 7, and then I have 8 repeated 4 times added together. So it will be 4 times 8, but then 8 is 2 times 4. So same as before, instead of writing it this way, I can write 2 times 4 to the power 2. So let's do it exactly like that, plus 2 times 4 to the power 2. 2 times 4 to the power 2. Now, if it wasn't an infinite series, if it was finite, we should not also, I want one other thing. It's easy to forget about this compound sort of series. We have a power of 2 here, so I need to keep it there, and we have a power of 3 here, so I need to keep that there as well. Okay, so if I continue doing this for, let's say, the one that ends up with n terms, so this is like 4 terms, this is like 3 terms in numerator denominator, the one that has n terms, I will end up with 1 plus 3 plus 5 if it was a finite version of, this is an infinite one because of these ellipses, but if it is supposed to be a finite one, I would have n terms in let's say numerator and denominator, and as you can see, when we have 4 terms, 7 is 2 times 4 minus 1. So when we have n terms, the last term, in the numerator is 2 times n minus 1. And of course, same idea. I can repeat that 1 plus 3 plus 5 plus 7 plus 2 times n minus 1. And then we have 2 times n to the power 2. Okay, so what can we learn from this? There is a very quick, easy trick to just quickly show the sum of these terms in numerator that is also appearing in denominator. That simple trick, this is basically what we have in numerator and denominator. This is just a simple arithmetic series. So this is simple arithmetic series. And it is with the initial term 1, final term 2n, so this is initial term, and this is final term. There are n terms. Final term 2n minus 1, there are n terms, and then common difference, meaning that with what value we are growing this arithmetic series. You can see that 1 gets to 3 when you add 2, 3 gets to 5 when you add 2, 5 gets to 7 when you add 2. So basically, arithmetic series with initial term 1, final term 2n minus 1, and then common difference, basically the delta between consecutive terms. So common difference equal to just 2. So that there is a formula for that. I'm not going to use that formula because it is very straightforward to prove this. The best way to prove it is like this. I'm going to say that the sum of 1 plus 3 plus 7 up to 2n minus 1 is just s. So keep it that way. 1 plus 3 plus 5 plus 7 plus dot dot dot. And then the last two terms I'm going to write is 2n minus 3 plus 2n minus 1. I can rewrite s. So write s one more time. S meaning that the result of this summation. I'm just writing it twice. Now, start from writing this sum in a reverse order. That doesn't change anything. So I'm going to write 2n minus 1 first. And I'm going to write 2n minus 3 next. I'm going to write the next one here that I'm not showing is 2n minus 5. And of course 2n minus 7. And if you keep using the ellipsis, as we have here, then we get, so we have the ellipsis, and then we have, of course, 3 showing up, and finally 1 showing up in the reverse order. Now, when in these two summations we add them together, in the left side of the sum we have 2 times s, s plus s, but then these terms one by one added together, 2n minus 1 plus 1 give us 2n. 2n minus 3 plus 3 give us 2n. And 2n minus 5 plus 5 gives us 2n. These two guys, they give us 2n, and this goes up to, say, again 2n and 2n. How many of these do we have? N of them, because we know that there are n terms. There are n terms in this arithmetic series. So what did we find? 2 times s is equal to n times 2n. So 2n squared. Therefore, what I learned is this is 2 times s. So s is n squared. This is well known, but it's good to just not make any assumption here and just proving it in using this little trick. So what I'm trying to say is for this general term of the series, and of course there is a power there, I'm not going to show it for now, but inside the close bracket, numerator is basically n squared. So this whole thing, let me change the color. This whole thing, in the numerator we have n squared. In the denominator we have again n squared, which is this repeated one, plus 2n squared. So interesting. Any term we consider, including this general nth term, looks like n squared over 3n squared. N squared cancels out and it becomes 1 over 3. Interesting, and that's exactly valid for everything. So 1 plus 3 over 5 plus 7 is 1 over 3. and 1 plus 3 plus 5 over 7 plus 9 over 7 plus 9 plus 11 is again 1 over 3. So all the terms in this infinite series, or even the finite version, is just 1 over 3 to some power. So the lesson we learned is our series of interest is in the form of, I'm gonna just write it here, so is in the form of 1 over 3 plus 1 over 3 to the power 2 plus 1 over 3 to the power 3, and these powers are just coming from what we had. See, in the given compound series we have powers that are showing up, so I'm just repeating them, and this goes on forever. Of course, if we are dealing with the finite version of this summation, it would go up to 1 over 3 to the power n. So in the finite version of the summation, what is this? This is now, so we had a arithmetic series with common difference. Now we have a geometric series with initial term 1 over 3, so initial term, and we have a common ratio, which means that with what multiplier we are getting to the next term. So we want to get to 1 over 3 to the power 2, so we are multiplying prior term with 1 over 3. So, and also we keep doing so from 1 over 3 to the power 2. How do we get to 1 over 3 to the power 3? By just multiplying by another 1 over 3. So we can see that any term to next term is just simply multiply 1 over 3. This is the classic definition of geometric series. As I said, 1 over 3 is initial term. In the finite version, 1 over 3 to the power n is final term, or ending term, and the common ratio is this constant multiplier that we are multiplying, so that's common ratio between two consecutive terms, that is fixed value. Okay, the formula for this finite sum is well known for geometric series, but I'm not going to even rely on that because it's super simple to prove the outcome, which we just do it this way. If we multiply the whole thing by 1 minus 1 over 3, or 1 minus r, what I'm going to get is multiply this and divide, of course. So I multiply and I divide. I'm not showing divide here, I'm going to show it here. But when you multiply this with the first term, we're going to get 1 over 3 minus 1 over 3 squared. You multiply this with the second term, you're going to get 1 over 3 squared minus 1 over 3 to the power 3. And do this with the third term, so you're going to get 1 over 3 to the power 3 minus 1 over 3 to the power 4, and so on and so forth. Last term multiplied by 1 minus 1 over 3, we're going to get 1 over 3 to the power n minus 1 over 3 to the power n plus 1. Denominator is this thing that we multiply with numerator. We need to put it in denominator to cancel it out. Okay, so the nice thing that is showing up is this cancels out this guy, this term cancels out this term, this cancels out next term, and this goes on up to this one. What remains is only standing 1 over 3 and minus 1 over 3 to the power n plus 1 in numerator. So basically we end up with 1 over 3 minus 1 over 3 to the power n plus 1, divide by, this one is 2 over 3. We can multiply numerator denominator with with let's say 3. We get 1 minus 1 over, or we can just summarize it this way. It becomes 0.5, 1 minus 1 over 3 to the power n. That is the closed form formula for the finite version of the overall summation. So I'm going to write it here. That is my closed form formula. So closed form formula for finite version of compound series or sum. Now, for the infinite version, because of ellipsis that says this goes up to infinity, all I need to do is very simple. Just take a limit of this when n goes to infinity. So the infinite series is evaluating to limit of 0.5 times 1 minus 1 over 3 to the power n when n goes to infinity. Obviously, when n goes to infinity, this term goes to 0 because 3 to the n is in denominator, and the whole thing just converges to 0.5. So all I'm trying to say is, with this analysis, basically we ended up answering the question that the answer is just simply 1 over 2 or 0.5 for this infinite series, which is effectively a compound, turned out to be a compound arithmetic series and geometric series, or geometric series that has a nested, it's sort of a nested geometric arithmetic series, and that's why we are referring to it as a compound infinite series. I hope this example is helpful in terms of showing how we can address these kind of series using some tricks so that we simplified and then we find the closed form formula for the finite version and then the answer and convergence for the infinite version. I hope this example is helpful.